Alright guys, this is your Unit 3 Quiz 2 study guide. I'm going to do the even problems, and you guys have the answers to the odds. Just make sure you guys show your work on the assignment so that you get your credit. But each even problem that I'm about ready to do should be able to help you out pretty decently with the problem before it. Alright, so let's go ahead and begin here. For number 2, when you're trying to find a limit, you usually start with just doing direct substitution, and we'll see if that works for us. So let's try that first. And I'm pretty sure that's what this problem is. It's one where you should be able just to do direct substitution, and it shouldn't create any problems. So let's see. The cube root of -1 is -1, and negative times -1 leaves me with a positive 1. So our final answer there would be 1. So this is a limit where basically you can find the limit by doing direct substitution, and the reason why you're able to do that is because cube root functions are continuous everywhere, and you could see that on the little sheet that I printed out for you guys. And so your number 1 will be the same. It's just a basic direct substitution type of problem. Alright, let's go ahead and take a look at the next even problem, number 4. This is a piecewise function, and I'm being asked to find a one-sided limit. I'm being asked to find the limit as x approaches 0 from the left. Now, if you're trying to approach 0 from the left, then you're going to use the part where x is less than 0. So I'll be doing direct substitution with this piece of the piecewise function. And so if we just plug 0 in for x, we end up with 4 as a final answer. Okay? So the only thing that's different about that one is the fact that you have to know which piece of the piecewise function to use based on whether you're approaching from the left or right. And that will help you with your number 3. Let's go ahead and take a look at number 6. For these particular problems, anytime you're being asked to find the limit, you're going to notice, first of all, if I try direct substitution, we're going to run into a problem. Oops. So we end up with 4 times the absolute value of 0 over 0, and that's undefined. So we can't even really say it equals that. You can't say it equals something undefined, but you can just say you can't use direct substitution. Now that doesn't mean that the limit doesn't exist. It just means that we can't find the limit by doing direct substitution. Okay? So there's another way we can handle this, and the main clue here is the fact that we're dealing with an absolute value function. Now, when you're trying to find the limit of an absolute value function, the best way you're going to want to approach that is by turning it into a piecewise function. And the way that we do that is by taking the part that's inside of the absolute value bars, setting it equal to 0, and solving for x. And that will tell us the place where the absolute value function changes signs. And so the absolute value function changes signs at x equals 2. And so now we make a number line, and we break that number line up into 2 halves with that changing point of x equals 2 in the middle. Anything to the left of that is what we're going to be calling x is less than 2, not 3. That's a typo. Or a right O, I guess, because I'm writing. And to the right of that will be anything where x is greater than 2. And so what I'm going to do for the left side is I'm going to pick a number that's actually less than 2, and I'm going to plug it in for x into the absolute value expression. So a number that's less than 2 would be something like 0. So if I plug that in, I end up with this, and as you can see, the absolute value of 2 isn't going to change the value of the 2. So to the left of 2, in other words, for all x less than 2, the absolute value will not change the signs. However, for x greater than 2, it probably will, because it usually does the opposite for the other ones. So let's just check, though, to be sure. So I'm going to pick a number bigger than 2 on this side. and that gives me -1. And the absolute value -1 will change to a +1, so the value will change there. And so now that we know that the values change on the right but not on the left, we're ready to go ahead and start writing out our piecewise function. So the first thing I'm going to do is I'm going to say we have two different intervals here, less than 2 and greater than 2. Now what I'm not allowed to do is I can't put equals 2 because we've already proven up here that you're not allowed to plug in 2. So I'm not going to put an equal sign on either one of these. But what we establish is that for all x less than 2 there is no change. So my function is going to stay exactly the same. I'm just going to change the absolute value bars now into parentheses. Okay? And then for all x greater than 2, we've established that that will change the signs. So now my expression, which looked like this before, will now have a negative in front of that absolute value. All right, which now is just a parenthesis. Okay, so there's my piecewise function. Now at this point, you'll notice that we could do something a little bit interesting. We can cancel out these x plus 2's. And so really all I can do now at this point is I can just kind of simplify the expression a little bit so it looks like this. And we're good to go. All right. So now what we can do is we can prove that the limit as x approaches 2 from the left of my function, which I'll just call it f of x. They don't really name the function for us here. And the limit of my function as I approach 2 from the right, we want to see if they're equal. Because if they're equal, well then we have good news. That means that the limit exists, and that would be our limit if they're the same. But if they're not the same, that means the limit doesn't exist. All right, so if I'm approaching 2 from the left, that means I'm approaching where x is less than 2, and the answer for that's going to end up being 4. And if I'm approaching 2 from the right, I'm approaching where x is greater, and that's -4. Now, as you can see, they're not the same. And since they're not the same, that would mean the limit does not exist. Okay? So, now that's not too uncommon with these types of questions, but that's usually how it ends up turning out. All right, let's go ahead and take a look at yet another question here, number 8. So, now, for the rest of the problems we're going to be looking at ways to remove some discontinuities, because for this problem here, if you tried plugging in 3, it's not going to work because it's going to make the bottom equal 0. And you'll have a similar thing happen for the next two problems. You can't plug in the number that they give you. But what makes each of these next 3 problems, 8, 10, and 12, different is the fact that you can still find the limit, and the way that you're going to find the limit is by removing the discontinuity. And each one of these is an example of how to remove the discontinuity in a different way. So for number 8, this one, as you can see, this one's not it's not a complex fraction, and it doesn't have any square roots. It's just a polynomial on top of a polynomial. When that happens, the way that you remove this discontinuity is by factoring. Now for this problem, we would factor the top. So I'm going to write this, the limit as x approaches 3. Got to know how to do that factoring once again. That's not going to go away. All right, so we asked ourselves, what times what makes x squared? Well, that would be x times x. And what times what makes 9? That's going to be 3 and 3. And one of those is a positive and a negative. That's what we call the difference of squares. Okay? Now, the next thing that we have is to remove the discontinuity. So these are going to cancel out. And so now I have this, the limit as x approaches 3 of negative x plus 3. Watch out for those little negatives hanging out in the front. They're easy to forget about, and then you'll end up with the wrong answers. You got to be careful there, but it's still there, so we're good. Once you've removed the discontinuity that we had there, now we can go ahead and plug in our 3, and we end up with -6 as our final answer. Okay, and so that's an example of how to remove a discontinuity by factoring. Let's go ahead and take a look at another one here. This one has a similar situation. Direct substitution's just not going to work. If you tried to plug in the number that they give you, it's going to fail. So I'm supposed to do number 10 though, which is a similar idea. But here's the difference. This one's not a factoring problem. It has square roots on it. And when there's square roots, the way that we deal with that is by doing a process known as rationalizing. Rationalizing means we want to get rid of the square root where it is right now. And the way you do that is by multiplying the bottom by the same exact expression, except instead of a minus 3, it's going to be a plus 3. And whatever you do to the bottom, of course, you need to do to the top. So I'm also going to multiply the top by that same thing. Now when I rewrite my limit, the top, I'm not going to really do anything special with that in this case. I don't want to FOIL that out or anything. It wouldn't help me. In fact, it would actually make things worse if we did that. So we're just going to leave this alone. But the bottom, the place where, in this case it's on the bottom, but it can also be on the top. But the place where you have two square roots being multiplied together, the conjugates multiplying each other, that's the one where you're going to multiply this thing times this thing, which is just going to give you x plus 6. And then this thing times this thing, which is going to give you minus 9. And now I don't want to rewrite all this, so if you don't mind, I'm just going to go ahead and erase it. But positive 6 and negative 9 can be combined together to make negative 3. And typically what you're going to find happen at that point is that you're going to be able to remove the discontinuity. So now that we've removed that discontinuity, we have the following. And we're ready for some direct substitution now. So if I go ahead and plug in, I'm going to end up with the square root of 3 plus 6 plus 3. Now that's 9, and the square root of 9 is 3. So we have 3 plus 3, which is 6, is my final answer there. Okay. Let's go ahead and take a look at another type of limit where there's a removable discontinuity. But for this one, we're going to remove the discontinuity in a third and different way. Instead of removing the discontinuity by factoring, or instead of removing it by rationalizing, this one we're just going to remove it by simplifying the expression. This is what we call a complex fraction. A complex fraction is one where you have a fraction inside of a fraction. And so we're going to just simplify that expression by multiplying every term, of which there are 3. Here's one term, here's another term, and here's another one. We're going to multiply all 3 of those by the little denominator that you see there, the 1 plus x. So I'm going to multiply this one by 1 plus x, of course. I'm going to multiply this one by 1 plus x. And I'm going to multiply this one by 1 plus x. Now, right here, these two cancel. And that leaves me with the following expression. Once again, I don't want to multiply on the top. I want to leave those separate. It helps us whenever we end up having to cancel and reduce stuff at the end. But we have 1 minus 1 parentheses 1 plus x. Now on the bottom here, though, we do want to simplify. I'm going to distribute. And it looks like these 1's cancel out. Now I've got x times 1 plus x over negative x. Now the x's are going to cancel each other out as well, but that negative's still there, so don't let that thing disappear on you. So I'm left with a negative and then a 1 plus x. Now I'm not going to, some of you guys might have wondered, well, Mr. Bailey, why'd you put it there? Why didn't you put the negative on the bottom? Well, that's weird. That doesn't even make sense. That's not even a real number, right? What that is that's a negative 1, right? So, I mean, if you want to leave it on the bottom, you can. It's just a negative 1. But when you divide by a negative 1, it just changes everything on the top to a negative. So I just moved it to the top myself. But if that was confusing to you, you can just leave it on the bottom. Just don't leave it as a negative. It's a negative 1. All right, from here, we're going to go ahead and do our direct substitution. So I'm going to plug that in. And I end up with 1 plus a negative 1 over negative 1. And, well, that's 0. Now, it's okay to have 0 on the top of a fraction. That just means that the answer is 0. And so the limit of this particular function here, as x approaches -1, is 0. All right? And so that was the third and final way for learning how to remove a discontinuity that we talked about in the preceding week. Let's go ahead and take a look at number 14. Find the value of a that makes the piecewise function continuous. So for these situations, what we want to do is we just want to do a limit from the left of this number and the same limit from the right. And for this thing to be continuous, the left and right limits need to be meeting up at a common point. And that would mean that the limits would be equal. Okay? And so let's go ahead and do this. So if I'm approaching 2 from the left, that would be this piece. And if I'm approaching 2 from the right, and if I'm approaching 2 from the right, I would use this piece. And then we do our direct substitution. So I'm going to plug in 2 here. If I plug in 2 there, I'm going to get 3 times 2, which is 6, minus 5, which is 1. Then I'm going to plug 2 in here. 2 squared is 4, so I'm going to end up with 4 times a. And then here, if I plug in 2, I'm going to get 4 and then minus 1, which is 3. So all I need to do now is solve for a. And then for this particular problem, I end up with -2/4, which is -1/2. So that would be the answer for a that would make this piecewise function continuous. All right, let's go ahead and take a look at number 16. Now this is going to be a free response question. Everything we've done so far on your quiz will end up being a multiple choice, but this one and the ones after it are all going to be free response questions. So these ones are not multiple choice questions. So I've given you a piecewise function, and the question is, determine if the function is continuous at the given point. Okay, so I want to know, is this function continuous at x equals 0? Well, in order for it to be continuous at x equals 0, we need a couple things to happen. F of 0 needs to exist, and the limit from the left needs to exist. The limit from the right needs to exist. And those two limits need to be equal, which means the limit exists. And furthermore, not only does the limit need to exist, but also the limit value needs to equal the function value at that point. So basically, we need to find f of 0, we need to find the limit from the left and the limit from the right, and all three of those things need to come out to equal the same thing. If they don't, then my function is not continuous at that point. So for f of 0, I'm going to find out where the equal sign is, and as you guys can see, my equal sign's right there. So that means I'm going to use this piece to find out what the function's value actually is at that point. So if I were to plug in 0, that would look like this, and I end up with 1. Okay? Now if I want to find the limit from the left of 0, that means we're looking for where x is less than 0, and so I'm going to be using this piece. And that gives me the square root of 1, which is 1. And then to find the limit from the right, we're looking for where x is greater than 0. And actually, I just realized there's a typo. I'll try to fix it. But it's supposed to say greater than 0 there. And where x is greater than 0 is where it's to the right, and so we'll be using that piece there. Now we've actually already plugged that in here once, so we're just going to get the same answer, of course. And so sure enough, all three of them are equal, and so we would say yes, it's continuous. Now if your answer is no, this is your work. So that would qualify as your explanation. So if you showed all your work like this, all you have to do is say, no, it's not continuous. And maybe it's because this didn't exist, or maybe it's because it didn't equal the other things, or maybe this didn't exist or it didn't equal the other things, or maybe this didn't exist or it didn't equal the other things. So if you just show your work like I did here, all you have to do at that point is say yes or no, and you're pretty good to go. Okay? Let's go ahead and take a look at our next problem here, number 18. Okay, so this one is also another free response question, and this is actually from Monday's lesson. We're trying to prove that a specific y value exists on an interval, and that's the intermediate value theorem. Okay, so how do we do that? Well, first of all, we want to identify our a value and our b value and our k value. So I'm trying to prove, now you guys don't need to graph this, I'm just doing this for the heck of it, but starting from x equals 0 up to x equals 2, I want to prove that somewhere along that interval my graph crosses the x-axis, because at the x-axis the y value equals 0, and that's my k. So I want to prove that somewhere it crosses the x-axis between 0 and 2. And so how do we do that? Well, step 1, as we've already done, is to identify the a, b, and k. Step 2 is to make sure that the function is continuous. Now, if you guys look at your Continuity of Common Functions worksheet from Lesson 3.3, Part 2, you'll see that exponential functions are always continuous. So this function's continuous everywhere. It doesn't have any holes, gaps, or jumps. So that's good to go. The next thing that we need to do is we need to find out what is f of a and what is f of b. We need to make sure that they're not the same. They have to come out to be different. After that, we'll need to make sure that our k value is between them as well. So in this case, for this problem, my a is 0, and for my b, it's 2. Now, f of 0 is going to be e to the 0 minus 2. Now, any number to the 0 power is always 1, and 1 minus 2 is negative 1. Now we'll do f of 2. Now I end up with e squared minus 2. Now, that's a weird number, and we don't really need to calculate it, because it's going to come out to be some positive number. Now, here's how I know it's going to be positive. I know that e is about 2.72. So already it's bigger than 2, and if I square it, it's going to get even bigger than 2, right? So if I take a number that's bigger than 2 and I subtract 2 from it, I'm still going to end up with a positive number. So I'm not even going to bother finding the value. Well, I guess I will. What the heck? I'm going to get out my calculator. I'm just going to do e squared minus 2. But you don't technically need to. The point is that it's going from a negative number to a positive number, and that's actually going to be enough for us to be able to answer the rest of the problem. But we'll do it anyway just for fun. Let's go ahead and find out what e squared minus 2 is really quick. So e to the second power minus 2 is 5.4 approximately. And so 5.4, oh, well, actually I already took the 2 away also. So I end up with 5.4. All right, so there it is. So notice that my f of a and f of b are different, so that's good. We need them to be different. Also notice that my k value of 0 needs to be between those numbers, and it is. So we're great. We've met all of our criteria. We found a, b, and k. We know it's continuous, and my k value is between the two f of a and f of b values. That means that the IVT applies. Now, before I write out my final answer here, I want to put it on the graph. Now, once again, you guys don't have to do any kind of graph on this exam. I'm just doing this for your teaching purposes. So, at x equals 0, y equals negative 1. So I'm going to put a dot right here at 0, negative 1. And at x equals 2, y equals 5.4, which would be like right about here-ish. Well, if this is a continuous line, which means I have to connect this dot to this dot with one continuous line that has no holes, gaps, or jumps, as you guys can see, somewhere along there, at some value of x, we'll call it c, the y value has to equal 0, right? And so this is how we write our answer. Since f of x is continuous and goes from -1 to 5.4 on the interval (0, 2), there must be some value c such that f of c is my given k value, which is 0. Okay? And that's just fancy math talk for saying, yeah, it's got to touch the x-axis somewhere. And that's it. All right? So that's number 18, your second free response question. Let's go ahead and see what else awaits us here. Now, for the last problems, what I'm going to do is I'm going to go ahead and do all of them. But let's go ahead and take a look at our instructions first. So this problem here says, for each problem below, explain why the IVT, the intermediate value theorem, cannot be applied to this function to prove that it has a 0 on the interval from -5 to 5. All right, so for these problems here, we have an a value of -5, a b value of 5, and a k value of 0. And basically, you need to tell me why you can't use the intermediate value theorem to guarantee that it actually touches the x-axis or has a y equals 0 value on the interval from -5 to 5. So the first thing you want to do is you want to check, is it continuous on the interval? So I'm going to write this down. Is the function continuous on -5, 5? In other words, are there any holes, gaps, or jumps for this function on that specific interval? The next thing is we want to make sure, is it true that f of -5 doesn't equal f of 5? Because we need that to be true. They can't be the same thing. The y value for -5 and the y value for x equals +5 cannot come out to be the same. So we need to make sure that that's true as well. And the final thing we need to check is we need to check, is the k value, which is 0, between, matter of fact, instead of writing all this out, I'll just write it a little bit differently. I'll say, is 0 in between f of b and a, okay, or f of -5 and +5. All three of those things have to be true if you want to use the IVT. Now, on all three of these problems, one of those things isn't going to happen, and we got to figure out which it is. All right? So here we go. Let's go ahead and take a look at the first one. Let's start off with our first question. Is it continuous on the interval? Well, cosine is always continuous, so that's not a problem. But notice that we do have an x in the denominator, and when you have a fraction, you're not allowed to have 0 in the bottom. So that means that x cannot equal 0. Now, is that number on this interval? In other words, is 0 on the interval from -5 to 5? Yes, it is. It's right in between those two numbers. And so we would say the intermediate value theorem cannot be applied to this problem because it has a discontinuity at x equals 0, which is on the interval -5 to 5. So we can't use the IVT on number 19 because it has a discontinuity at x equals 0, which is on the interval that we actually are trying to use the theorem for. All right, so that's number 19. Let's go ahead and take a look at number 20. So for number 20, is it continuous on the interval from -5 to 5? Well, that's a polynomial. Polynomials are continuous everywhere. So far we're good. Check. Let's go ahead and keep checking on though. Is it true that f of -5 is equal to, or is not equal to f of 5? Well, let's see. F of -5 and f of 5. F of -5 means we're going to take -5 and we're going to square it. And f of 5, you take 5 and square it. And that's 25. And that's 25. Uh-oh. Those are equal. So we failed there. And as a result, we're going to say that we cannot use the IVT. So for this one, number 20, we're going to say we cannot use the IVT because f of -5 is equal to 5. They're not allowed to be like that if you want to use the IVT. They have to be different values. You guys probably already know what's coming up on the last one, but let's go ahead and do it anyway just to kind of see it happen. All right, so is it continuous? Yes, it is. It's a polynomial. Check. Is f of -5 not equal to f of 5? Well, let's see. F of -5 and f of 5. F of -5 is -5 plus 6, which is 1. And f of 5 is going to be 5 plus 6, which is 11. So those are not equal, which is good. So far we're doing good. The last thing we want to do is we want to check to see, is 0 in between those two values? So is it true that 0 lies in between 1 and 11? And the answer is no, that's not true. So we fail there. And we would say the reason that you cannot apply the IVT to this function on this interval to prove that y equals 0 at that somewhere on that interval is because the 0 is not in between the f of -5 and the f of 5. Well, I don't like how I wrote that. That's saying it is equal, so I don't want to do that. So we'll just say it differently. Sorry. Let me rewrite that. So because 0 is not between f of -5 and f of 5. So those are the three reasons why a function may not be able to have the intermediate value theorem applied to it on a specific interval. All right, and I think that closes it out. So hopefully that was helpful, and we'll see you tomorrow. Good luck on your quiz.